In the last video, we have defined the geometric product from a vector x to a vector y, like here. Or we can simply say that the vector x geometric product vector y. However, this definition is only defined on from a vector to a vector. And we want to make the geometric product more universal by redefining it such that we can take, for example, bivector geometric product with a vector, or a vector geometric product with a bivector. Or we can also have a scalar geometric product with a bivector geometric product with a scalar, or a scalar geometric product with a vector, or a vector geometric product with a scalar. So in this video, we will redefine the geometric product in a more general way and derive different property from the new definition we have. And we will also see that we will get exactly the same case when we have from the new definition, when we have a vector geometric product to another vector that will completely equal to our old definition, which means the new definition is more general, but it doesn't change from our new definition when we have a vector geometric product to another vector. Now we introduce the more general definition of geometric product, which it will be defined in terms of algebraic definition. So before we go to the definition here, we would like to specify the symbol we use. So alpha and beta, which the Greek symbol will indicate scalar, and normal English alphabet with the arrow on the top indicate vectors, and the capital English alphabet A, B, C can be anything. It can be scalar, it can be vector, it can be bivector, and it can be trivector, fourth vector, and so on. But trivector, fourth vector, such thing we will not touch in this course. So now we go into the definition of geometric product. So we define the geometric product with the following property, and we will have 5 different property, and these property are defined such way so that we cannot derive from another things, but they are defined in such way. First is the scalars definition. So if we have a scalar, the geometric product from a scalar to anything, it will be equal to anything. It can be scalar, it can be vector, it can be bivector. By anything, I mean it will be equal to the anything geometric product to scalar. So the order doesn't matter in this case. And the second thing, scalar square, which means that the geometric product from a vector to the same vector will equal to some sort of measurement, and this measurement will give us a scalar. And in our video, we will specify that this kind of measurement is a dot product in our case here. So maybe just tell that this belongs to number 2. Draw a line here. Yes, so this property is belong to the number. This statement is belongs to the number 2. So number 3, distributivity and linearity. That's the thing we want to have. And I don't think I need to explain a lot here, so you can just see the formula. And 4, associativity. This tells us that the order we do the geometric product, which one we perform first. We perform BC first, then from A to the BC, or we perform AB first, then from AB to C, it will be the same. And 5, which I think is very important, is that the commutativity is not required. This means that AB may or may not equal to BA, and this is very important, and keep it in mind, because many products you met in your life, it is actually commute, but this one, a geometric product, they generally don't commute. In this slide, we want to show that the relation between dot product and geometric product can be given in this equation, so that we can, when we have a dot product from a vector to a vector, it can be expressed into a geometric product 1.5 and parentheses from x to y and plus from y to x. So let's try to derive this relation. First, we use a dot product that multiply dot product with in this relation, and then we try to expand this equation. So you will have x dot x plus x dot y plus y dot x plus y dot y. And we know that the dot product is the dot product actually commute, so we can, so this means that this part, this part is actually equal to x dot y. So we can write it in x dot x plus 2x dot y plus y dot y. And if we change the if we throw this and this to the left side and divide it by half, what we get is that we get x plus y dot x plus y minus x minus y equal to 1.5, the whole thing, x dot y. And then we usually want to express this on the left and the whole thing here to the right. So let's change a little bit. We just rewrite this. Okay, maybe we can move it here. It's equal to x dot y. So from the, if you remember our algebraic definition of the geometric product, the algebraic definition of the geometric product is that we have a scalar square property. So for if x, when I say x, I mean geometric product from x to x is always equal to some measurement, the x dot x, the this Q mean measurement, and in our case, in this course, we say that the Q is actually mean dot product. So we use this property. Then we have if we use this property, then what we have is this one. Now this is x plus y, geometric product x plus y, and this minus is it's an x plus this is also x plus y and minus x, no sorry, then minus y. Oh, sorry, here should be dot here. Yeah, so we actually get this. Then we have 1.5, and then we expand this between these two parentheses. Then we get, so xx the reason we can distribute is that geometric product was is defined that geometric product is defined that is distributive. So we can have xy and yx and plus yy, the whole thing, and then minus xx and minus yy, and you see that these will cancel out because this is a geometric product from x to x and minus geometric product from x to x. And the same thing here. Then we end up with 1.5 xy plus yx. And remember, in geometric product, they generally do not commute. So xy and yx may be different. You will get different answer from the geometric product. So that's why the order in geometric product is important. And one more thing is that notice everything in here is geometric product, but those things here are the dot product. So they are not the same. In this slide, we will show that when we have an orthogonal basis of a normal basis vector, and we are using two basis vector that is orthogonal to each other, and the geometric product between them is equal to the minus sign when we swap the order of the original geometric product. So this mean that this mean that when we have a E1, the 90 degree with ej, when we have a E1 geometric product to ej is equal to minus ej geometric product to ei. Okay, ei, not E1, sorry. Ei geometric product to ej is equal to minus ej geometric product to ei. And how can we prove this relation? So first, we assume that we are using of a normal basis, which means that the dot product between the dot product between different bases is a 0, and the dot product with itself is 1. Then let us write the geometric product ei ej, and we can add the ei ej is equal to the ei ej, which doesn't tell us anything, of course, but we can also write it that way, like 1.5 ei 1.5 ej plus 1.5 ei 1.5 ej, and plus 0, which nothing. But instead we write 0. We can also write 1.5 ej. The order is, we swap the order, and ei minus 1.5 ej, and ei. And remember here, the sum of between these two are zero. Sorry, not -1 but 0. And what we can do is we swap out a little bit. So we change these two, swap the order, so that we get 1.5 ei ej plus 1.5 ej ei and plus 1.5 ei ej minus 1.5 ej ei. Remember that from the last slide we have this thing equal to dot product. This thing, sorry, not 1/2. This thing equal to ei dot ej, the dot product, which we know from here that is 0. But let us finish the equation first. This whole thing is equal to 0. So what we left is 1.5 e1 ei ej, not plus, minus, sorry, minus ej ei and then if we compare this relation to this, since they have to be equal, then what we get is this is minus, then okay, yeah, then 1.5 ej equal to 1.5 minus 1.5 ej ei. This means that ei ej is equal to minus ej ei and clearly we can see that this relation give exactly the this relation is antisymmetry, and it is exactly equal to the case we have a wedge product, such that ei wedge ej equal to minus ej wedge ei. However, in wedge product, generally speaking, any vector, let A and B are not necessarily orthogonal. A wedge B are equal to minus B wedge A, but that is not the case necessarily when we have vector A, B. From A to B mean the geometric product from A to B are equal to minus B to A. This generally not holds unless A is a 90 degree to A is a 90 degree to B, and this will happen when we have orthogonal. This is why we use the orthogonal basis to derive this relation instead of using a normal vector, because in geometric product in geometric product, this relation happen when you have a 90-degree between when two vectors are orthogonal to each other. Now we want to compare our new definition to our old definition. And just remind you that the reason we have the new definition of geometric product is that we want our geometric product not just defined between vectors. We want it also defined between a scalar vector, vector to bivector, and so on. But however, our old definition is only defined between a vector to a vector. So this is our old definition. I'm not going to repeat it. And let us see that we will use what happens if we use the new definition with the geometric algebra, with the geometric product, and see what kind of answer we will get. So we are interested in the case of 2D. We have a vector A and vector B, like we use a orthonormal basis. Vector A is A1 E1 plus A2 E2, and vector B is a B1 E1 plus B2 E2. Then we geometric product them from A to B using the new definition. We will get first, let us just write it out. A1 B1 E1 E1 plus A1 B2 E1 B2 plus A2 E2 E1. No, sorry, A2 B1 E2 E1 and plus A2 B2 E2 E2. And from this, we know that from the scalar square, we know that geometric product between two vectors that are the same is equal to some way to measure, and we use the dot product to measure them. So these two guys will become 1. Oh, sorry. These two guys become 1. And we also know that from the previous slide, we also know that E2 E1 is just equal to minus E1 E2. Then we use this to rewrite this equation. Is equal to E1 plus B1. No, A1 plus B1. No, sorry. A1 B1 plus A2 B2. And then plus A1 B2 minus A2 B1 and E1 E2. So here we will have a scalar 1, and here we will have E1 E2. And and for in the further video, we will like to write this bivector in a more compact form. So we will write for example, E2 E1 is equal to E21. Oh no, sorry, this is supposed to be E1 E2. Yeah, then we will write E1 E2 is actually defined as E1 E2, just a notation. This is just a notation. And if you see that from here, it's not far from that we have the old definition. We will get from the old definition, we will get E1 E2 B1 B2 plus A1 into minus A2 B1, and we have E1 wedge E2. But since remember from the last slide that if geometric product and the wedge product, if those vectors are orthogonal, and then they would behave exactly the same. So that our new definition actually is actually aligned with our old definition. However, then now this is now we have tested only between vector. We will test about what happened when we have vector multiplied by vector and in geometric product, and this is the whole reason we want to introduce the new definition, right? In this slide, we will explore the geometric product between vectors and bivectors. So we will look at 3 different cases. First is the vector multiply from a vector to a bivector, which is eiei to ejei. And second is bivector to vector, which is eji to ei. And the third is the a vector to a bivector, but have the vector don't have the same index with the bivector, which ek, eji. So let us look at the first case. So from ei, eji is just equal to ei, ej, ei, because this bivector just a short notation, then parentheses. And since geometric product is associative, we can we just first swap the index like we have learned before, because they are orthogonal bases. So what we can do is minus ei, ej, and then we can put this minus sign in front because they are associative. So it's equally we calculate the first two vector, then ej. Then since these two are equal to 1, so it's equal to minus ej. Now look at the second case. We will have eji, ei, and this is quite obvious because ej, ei, and now we have the same index here. We can, since it's associative, we can calculate these two first. Then they are 1, so we get ej. Because before we go to the third option, before we go to the third case, we would like to talk about what is the interpretation of 1 and 2. Some people will argue that, well, it looks pretty like rotation if we have this is called ej and this is called ei. No, this called ei. Then it seems like ei, ej, ei means counterclockwise rotation, because when we have ei, eji, it gives us this. It give up this a minus ej. So this is counterclockwise. Oh, no, it's actually clockwise. Sorry. when you apply this, it's like a clockwise. So then ei was pointing in this direction. After multiply with this bivector, then it is pointing down. But does it really like a counterclockwise? Does it really like a clockwise rotation? Because when we have ejei, when we multiply from the left side, the bivector multiply from the left side to the vector ei, we get ej. So this time, it seems like this time seems like a clockwise, counterclockwise rotation. So you might think, okay, so we can think about that these two things represent rotation. How it rotates clockwise or counterclockwise depends where you apply in the formula. So this bivector can rotate any vector to clockwise and counterclockwise. However, I will say that we don't think about this thing. The case 1 and 2, the bivector represent rotation. I will advise you I will advise you not think about that, because when you have a vector, like in our case 3, when you have a vector that does not share the same index with I and j, which does not laying in the ij plane, the k this does not represent any rotation. So what we get from case 3 is that ek, ei, ej, then that's it. That's it. When geometric product, you will get something called a trivector that we are not going to talk too much in this course. But yeah, so very important that in general, this is not how you do a rotation. In general, which we will talk about it later. In general, that we will have a vector. If we want to rotate respect to the twice of the degree between another vector, we will have this that assume the u and w has a unit length 1, and then we will rotate twice of the vector from w to u. But this will come later. Come later. And this is the way to rotate a vector in general in any dimension. But here you only see the 2 dimension. Then you think about, the bivector represent the bivector is represent rotation. It is responsible to rotation, but not all of them. We will come to this later, so I don't want to make this too complicated. So we will come to this later, but currently you don't need to think about geometric interpretation. Instead, just follow the algebraic definition of the geometric product and plug it in, and you need to, if they share the same index but not close to each other, then you need to swap them and get close to each other. Then you get the scalar, then you get back a vector. Yeah. So in these 2 cases, you get a vector, but this case you get a trivector. So it's a vector, a geometric product between a vector and bivector is not always representing rotation, and we will talk about rotation later. in this series of video.